Thank you, Josh. All right, so let's stay awake because we still have two more talks, and one of them is mine, and it's about exciting KCRM science, early science from KCRM. So I'm Yuguang Chen from UC Davis, and this work has been made possible, and also so Tucker joins here is very crucial to this work, and also Ryan Sanders, who just moved from Davis to Kentucky. I don't know why. It's also very crucial to this work. So I'm glad that I don't have to go into details about why chemical evolution of galaxies is very important. But again, I'm just gonna go briefly. We are able to measure the metallicity of star-forming galaxies now with JWST out to very high redshift. So this is from recent work from JWST about basically the mass metallicity relationship in the ISM. And what this really probe is that we can actually compare the chemical evolution in the interstellar medium with existing models. And these, by measuring for example, the oxygen to hydrogen abundance, we are actually really probing the star formation history and also the gas flows, the inflows and outflows of gas from feedback. So that's why the single metallicity of oxygen to hydrogen is very important. What I'm going to show you, what's more important is the ratio between different metals. So for example, in this talk, I'm going to talk about nitrogen to oxygen ratio. So the reason is that, for example, nitrogen and oxygen reacts differently to the history of star formation, right? So early on, you have in the history of a galaxy, you have core-class supernovae that basically keeps the nitrogen to oxygen ratio close to a constant, but then later on, when the AGB starts to blow out a lot of winds, it blows out of nitrogen. That increases the nitrogen to oxygen ratio. One of the recent discoveries with JWST is that we actually, when we go very high into the redshift, for example, this GNZ11 thing with JWST, is that you started to see very weird nitrogen to oxygen ratios. And there are lots of theoretical models trying to probe why. For example, this one, if you just take these numbers off the chart. So why? And there are a lot of theories, but as an observer, I want to make sure the measurements are accurate. So one of the issues with measuring metallicity in the ISM is that we rely on the emission lines. And that causes the abundance discrepancy. So if you measure using direct methods, one is from the collisionally excited lines, and the other one uses the recombination lines, and measuring the same kind of gas, O++, you actually, in the nearby systems, you can actually see this offset, the 0.2 dex offset between the two measurements. These are supposed to be very direct measurements. It's just atomic physics. So the explanation here, historically, is that there's temperature fluctuation. So the collisionally excited lines are these ones that are very sensitive to temperature. So the emissivity, the thing you see, will be biased toward high temperature gas because they're just more emissive. And recombination lines here, they are less sensitive to temperature, so they're considered accurate. However, there's no direct test to this explanation until very recently. Is that one way of doing direct tests is to use the far infrared fine structure lines. So these lines are actually also collisionally excited, but they are have a similar emissivity curve to temperature as the recombination lines. So we're trying to eliminate one layer of uncertainty if basically the emission mechanism may cause the difference here. So, and this is particularly important now because now at redshift starts to have ALMA observations of these far infrared lines at very high redshift 8.5, for example. So we ought to understand different metallicity measurement methods. Do they have different biases? Are we actually comparing apples to apples? So we did a direct test earlier this year using the data from KCWI before the KCRM, the red channel upgrade. So we use KCWI to observe Markarian 71, which is a very close high redshift galaxy analog. It's this, and it's very young, has very low metallicity, and its particular is very dust poor. We observed it with KCWI. We also observed with SOFIA, so the Boeing 747 telescope, and the Herschel packs. That's from archival data. So the reason we need, all of these three instruments are IFUs. And the reason we use IFUs is because we are spared with the complexity, the systematic uncertainties of aperture matching with IFUs. So we can actually literally convolve the spatial resolutions among the three different, very different wavelengths of instruments, and also do a fair comparison in the same apertures. So we got a surprising result. So I remember both Tucker and I, when we saw this result, first reaction, we were very excited. But the second reaction is like, oh God, when we publish this one, we're gonna be in deep trouble because some people are gonna be very unhappy about this. So the surprising result is that, so here on the left, this is the KCWI spectrum we took before the basically upgrade of the KCRM. On the right, these are the far infrared, so this is from SOFIA, this is from PAX, of the two O3 emission lines. So red one is the optical collisionally excited metallicity you measure. Magenta, that's the recombination line. So the difference here, not surprisingly, that's the abundance discrepancy, all right? So remember, if the temperature fluctuation is the cause of this discrepancy, we are expecting the infrared metallicity to be consistent with the upper value, not the lower value. But in this case, in this measurement, this particular object, Markarian 71, we found the opposite. It's actually the infrared metallicity is about 2 sigma inconsistent with the recombination line. Does this mean that, so this definitely means the temperature fluctuation is not the main cause for the abundance discrepancy, at least for this object. But further raise the question of, what about the other objects? And what about other kind of tests? That's why KCRM is so amazing. It opens up a different channel for us to directly do this test. And we are able to get the nitrogen 2. So all of these previous measurements are focused on oxygen. But now with KCRM, we are actually starts to probe different kind of gas, different ionization. So these different curves are from optical, collisionally excited, far infrared fine structure lines, so the recombination lines of oxygen-3. But for nitrogen 2, we don't have recombination lines, but for the other two, you have similar reaction, similar to oxygen-3. So amazing KCRM data. Special thanks to all of the KCRM commissioning team. So Nick and Rosalie are here somewhere, who took these data for us. So this is the KCWI field view. This is like a 3D view of the data queue we got. So these are nitrogen 2, H alpha, helium 1, sulfur 2, amazing data. And most importantly, we also get the fainter auroral emission, allowing us to have a direct measurements of the nitrogen 2 abundance as well. So here's the result. On the left, again, this is for HARO 3, a different object, but this is basically, again, optical CEL, recombination lines, and infrared ones. So for this one, we actually saw some temperature fluctuation. So the infrared one has some difference to the optical collisionally excited lines, but it's not enough to explain the entire ADF. Furthermore, if you add the nitrogen 2 here, it gets actually weirder. The reason I say that is that, so here, this blue one is from the nitrogen 2 122 micron far infrared emission. This one is from the direct optical CEL measurements. So if you compare these two, and just assuming, okay, so if there's a nitrogen 2 recombination, nitrogen 1 recombination line, we just plot it over there. The magenta one gives the temperature fluctuation gives us a magenta 1. That's not enough to explain the discrepancy. So we're actually in the opposite regime now. And the temperature fluctuation required in this case, it's ridiculously high. It's about 3,000 Kelvin. And if you have you see temperature measurements right here, that's about half of the sigma of the temperature fluctuation is about half of the actual temperature. So that's a lot. So if you don't trust the flux calibration between the infrared measurements and the optical measurements, fine, because this one should be more trustworthy. We're comparing infrared to infrared and optical to optical. So these ones are all from the infrared, so the N2O ratio directly from the infrared. There's no optical spectrum involved. This one is directly from the optical. There's no infrared spectrum involved. And you can see that the infrared N2O ratio is actually opposite to the temperature fluctuation. So what could possibly go wrong here? Maybe the far infrared. So one of the most immediate answer to us is that the far infrared aperture just contains more high metallicity gas. It's possible. And the most likely scenario is that the dust is correlated with high metallicity gas. So we are actually optical. The reason we measure lower metallicity is because the dust obscures a certain level of high metallicity gas. Is the temperature fluctuation from the nitrogen plus higher, much higher than the temperature fluctuations of oxygen plus plus? It's possible, but we don't know. So further test, the goal here is toward accurate interstellar metallicity measurements. So unfortunately, SOFIA decommissioned in 2022. So we are not very possible to obtain new data, but it left with amazing archival data, and also so is Herschel. So added with KCRM capacity, we can actually start to observe about 30 targets in the next year or so. We have a pilot study with Palomar CWI in early 2023. This is from Palomar CWI spectrum. These are archival far infrared ones. And we starts to actually observe many of more targets in the sample. So stay tuned. Finally, happy 30th birthday. And thank you everyone for making Keck possible. So I was born in 1993, exactly the same year as Keck. So growing up in the 2000s and also in the 1990s, so this is just to show how far-reaching Keck is back in the day. So this is like the go-to magazine for amateur astronomers in China. And this is a special issue in 2001 in March about 21st century telescopes. And there are 2 articles about Keck. And special thanks to editor Feng Chong, who I messaged last night to pull this out. But yes, it's an amazing telescope. I'm very happy to be part of it. So I'll leave summary and take questions.